an icy wind blows over the permafrost on the desolate Kola Peninsula. This is an unforgiving landscape, barren and isolated. But it is where the Soviet Union hoped to make history. Inside a small concrete overstructure with corrugated iron panels rattling in the wind, a huge drill bit, more than 20 centimeters in diameter, is lowered towards the ground and begins to descend. The year is 1970, and the Cold War race for technological supremacy between the US and Soviet superpowers is, according to some, over. The Americans beat the Reds to the moon the previous summer, and space is now adorned with stars and stripes. The Russian cosmonauts are forever runners-up. But there is another, lesser-known Cold War contest that the Soviets can still win. One not focused up, towards the stars, but down, into the Earth. To drill to the bottom of the Earth's crust, reach the mantle. The Russians' prospects are good, since the US abandoned their attempt 4 years earlier. Just as with the race to the moon, the motivation for digging to the bottom of the crust was ostensibly a scientific one. Although we have rocks that have been uplifted, altered and fractured from the top of the mantle, we don't have any fresh samples from this huge shell of scorching, flowing rock. Geologists don't know for sure its composition, temperature, or dynamics. For that reason, the Americans began an ambitious project in 1958 to drill deeper than ever before, to reach the Mohorovicic discontinuity, known as the MOHO, which is the boundary between the mantle and the crust. For this so-called Project MOHO, they chose to drill into the sea floor, where the oceanic crust is thinner. Unfortunately, that meant drilling from a floating platform on the open ocean, something that is common now but had never been done before. The development costs soared and the project was abandoned in 1966. They had drilled just 183 meters down. So, in 1970, the Soviets began their own effort to reach the MOHO. They only needed to drill deeper than 183 meters to decisively beat the Americans at this Earth race. On the stable Arctic ground of the Kola Peninsula, it was a simple prospect. Here, the crust is much thicker, up to 30 kilometers of rock lies between the surface and the MOHO, but there were none of the difficulties of drilling at sea. The Russians could take it slow and steady, inching down through rock layers until their goal was in sight. The Kola Super Deep Borehole is only 20 centimeters wide, but it passes through 12 kilometers, the deepest man-made hole on the planet. And these super deep rocks give scientists an incredible timeline view of the early Earth. And at around 2 billion years old, these rocks have been folded, faulted and squeezed, metamorphosed into new forms. But they can still be reconstructed to give a glimpse of the environments of their formation. There are the remnants of volcanoes, river and ocean sediments, even organic microfossils. It reveals a surprisingly normal picture of Earth, almost recognizable. And yet elsewhere, rocks from just 100 million years earlier tell a very different story, of chemical and climatic catastrophe that brought the entire living planet to its knees. This begs the question: how did the Earth transform from this barren rock to the beginnings of the world we know today? And was the Earth 2 billion years ago really as idyllic as the rocks seem to show? This video is sponsored by Magellan TV, the documentary streaming service. Big thanks to everyone who's subscribed to the new channel, and if you haven't, check it out. mind-melting stuff. And as with History of the Earth, it pairs very well with Magellan TV. Magellan has a huge range of documentaries on a huge range of topics, from dinosaurs to the edge of theoretical physics. One example we enjoyed recently was Earth in 1,000 Years, a fascinating insight into what the future holds for our planet. A great companion piece for this video, and one of more than 3,000 documentaries available. And you can now take advantage of an exclusive offer, 30% off an annual membership. This gives you an entire year for less than $3.50 a month, even if you've joined Magellan before and lapsed. You can simply click on the link in the description to claim your discounted membership today. Thanks. Viewed from afar, the early Proterozoic Earth looked dead. At 2 billion years old, the Earth is only just past half its current age, barely further from the moment of its formation as it is from today. It has been through extremes of temperature, from the molten heat of its formation to the gripping cold of a global ice age. On this watery ball of rock, the most unlikely thing happened. Life evolved. That life learned to thrive in all the environments Earth had to offer, invented new ways of getting energy, and almost killed itself in the process through chemical, then climatic catastrophe. The global Huronian glaciation had been triggered by the photosynthetic release of oxygen into the atmosphere, stripping the air of its most potent greenhouse gas, methane, while the photosynthetic bacteria continued to gobble carbon dioxide, thinning the planet's insulating blanket even further. Now, exposed to the weak rays of a still young sun, the planet was chilled to its equator. Oceans, once resplendent in blue and green, were covered by quiet, still sea ice. Ice covered the land too, as the last of the clouds deposited their icy loads over high peaks. What was next for the surface of the planet, trapped inside this seemingly eternal icy prison? 2 years after Soviet drilling began in the Arctic, French engineers discovered a 2-billion-year-old mystery in rocks close to the equator. Solving that mystery would help to shed light on a Proterozoic world emerging from cryostasis. The Pierre-Latte nuclear processing plant on the banks of the Rhône in southeastern France was a facility dedicated to enriching uranium from its mined ores for use in power plants and nuclear weapons. Thanks to the escalations of the Cold War, scientists understood the properties of uranium and its ores pretty well by 1972. They knew, for example, that every natural source of uranium on Earth, in meteorites and on the Moon, had 3 uranium isotopes, versions of the same element with slightly different masses, and these were always in the same ratio. The most radioactive, uranium-235, always made up 0.72% of the total. So, the French engineers were puzzled to discover that a batch of uranium from their mines in Gabon contained less than this, only 0.6%. The difference may be small, but it was unheard of anywhere else on or off the planet. From one source, up to 200 kilograms of uranium seemed to be missing, enough to make a dozen nuclear warheads. Geologists were sent to the Oklo mine in Gabon to investigate this worrying discrepancy. But they found no misconduct, no uranium theft. Instead, they uncovered a remarkable natural phenomenon, a natural nuclear reactor deep in the Proterozoic rocks that had been smouldering away for hundreds of thousands of years. The heavy element uranium is formed under special conditions when stars explode in devastating supernova. When the Earth first formed around the newly ignited Sun, it captured free-floating uranium from the swirling disk of dust and gas that writhed around the young star. And so, our planet is filled with it, inside and out. But uranium is of greatest interest to us humans when it is concentrated further, allowing us to easily extract its ores for use in our energy-hungry, warring civilizations. One of the best ways for uranium to be gathered together and concentrated is through the vast cycling of rocks and water through the surface layers of the Earth. The element can dissolve in water and be transported along with river sediments or through hydrothermal plumbing systems that surround volcanoes. At the Oklo mine in Gabon, the uranium had been gathered together by mineralizing volcanic fluids that flowed through truly ancient sedimentary rocks rich in organic carbon. And around 2 billion years ago, tectonic forces began to uplift these rocks towards the surface, along with their uranium mineral veins. It appeared that the particular natural processes operating here were enough to concentrate the uranium-235 to far higher levels than is normally found. As they were uplifted towards the surface, groundwater would penetrate the rocks and surround the uranium. The water acts to slow down the neutron products of radioactive decay, keeping them close and helping to trigger a chain reaction within the densely concentrated uranium deposit. And so, a self-sustaining nuclear reaction could continue naturally. For a while. Eventually, the heat released by the ongoing decay would be enough to boil the mediating water, creating powerful plumes of radioactive steam that burst out of the Earth's surface like toxic geysers. When these yellow-ringed geysers erupt, the reaction underground slows to a halt. Without the water to sustain the fission, the decay products fly harmlessly away. And so this continued, in pulses of fission that lasted 30 minutes. This faithful cycle continued for hundreds of millennia, until the uranium at Oklo, once so rich, was depleted below natural levels, and the natural reactor fell silent forever. The discovery of a 2 billion-year-old nuclear reactor in the rocks of Gabon was groundbreaking, confirming theories made decades earlier, but as well as giving us a window into a bizarre and dynamic environment that existed 2,000 million years ago, they also tell us a lot about normal Earth processes at this time. There were stable sedimentary environments like rivers, deltas, and shallow ocean basins where living things lived and died in great numbers to enrich the sediments in organic carbon. These sediments and their resulting rocks are suffused with hydrothermal and volcanic plumbing systems, which concentrate rare minerals and alter the chemistry of the very rocks they penetrate. And tectonic forces continually warp these rocks as they are formed, forcing them deeper down into the crust or uplifting them to the surface, where they are exposed to water, air, and biological attack. That all may sound familiar. Indeed, they are the very processes that shape the surface of our planet today. But they are a surprise, coming so soon after the vicious Huronian Big Freeze. Although Gabon doesn't tell us how, it shows us that 2 billion years ago, the Earth does emerge. It has been covered by ice from pole to equator for hundreds of millions of years. Life has struggled on where it could. But now, thanks to forces hidden deep within the Earth, the tide is quite literally beginning to turn. In the grip of the Huronian glaciation, there are only a few places where any activity could be seen. For beneath the silent surface of the ice, the interior of the planet is still incredibly hot. Volcanoes pierce through the shell, flashing orange lava that cools to black rock and spews grey ash over the pristine white surface. Water bodies close to these volcanic pustules are warm enough to stave off the encroaching ice and become refugia for the 1% of life that clung on, desperately, through the endless winter. The volcanoes that punch through the surface are the outward expression of huge and slow tectonic forces gradually transforming the crust. Great rafts of rock bump together and grind, powered by horizontal convection within the roiling mantle. Where one slips beneath another, gravity tugs at the suspended slab, pulling the rest of the raft sideways behind it. These so-called subducting margins are the key to plate tectonics. And throughout the Huronian glaciation, hidden beneath the ice, plate tectonics is reconfiguring the first continental masses over hundreds of millions of years. Although scientists aren't certain when exactly true plate tectonics was established, the rocks that remain from this time, from Gabon and from the Kola Peninsula, among others, bear the telltale signs of this continental dance. The earliest volcanoes on the Earth would have been black, shallow shields, like those on Hawaii and Iceland today, formed by lava that flowed freely, following the slightest gradient and flooding far from the source before they froze solid. Where plates collide, they engage in a tectonic sumo that crumples and thickens the crust, lifting up mountain ranges and forcing down roots that plunge tens of kilometers further into the mantle. At subducting margins, water released from the doomed slab melts the mantle around it, creating magma that flows upwards and into the mountain's roots. This magma cannot escape so easily, and it sits buried at the heart of the mountain for hundreds of thousands of years. Its dark-coloured, heavy minerals crystallize and sink to the bottom, leaving behind a new kind of magma that is paler, stickier, and infused with gas. When this magma eventually reaches the surface, it creates a very different kind of volcano. When the lava flows, it doesn't make it far before cooling and stopping, building up huge, conical piles. And the pressure from magma and gas continue to build until devastating explosions blow the volcanic pile apart. These eruptions sound out around half the globe and loft ash and noxious vapors high into the sky to be carried great distances by fast jet streams. In this way, these stratovolcanoes build up tall cones and blow themselves apart time and time again. While we know these thickened volcanic ranges existed, the fragmented geological remains from this time make it difficult to know exactly how the early continents were arranged. Geologists look closely at the volcanic and metamorphic rocks from 2 billion years ago to reconstruct the collisions that must have formed them and the continental fragments involved in those conjunctions. And there is growing evidence that almost all of the continental landmasses were compressed together to form one huge supercontinent, known as Columbia. Researchers believe Columbia spanned some 13,000 kilometers north to south, larger than modern-day Eurasia, from Portugal to the Bering Strait. For much of the early Proterozoic, though, this impressive supercontinent was still covered in ice. The bright white of glaciers, ice caps and ice shelves only serves to reflect the sun's heat back into space, prolonging the chill for millions of years more than any normal ice age. It seems hard to believe that the planet will ever be able to break free. But the hot interior is to be Earth's saviour. With each continental collision, with each new explosive volcano, water vapour and carbon dioxide is being pumped back into the atmosphere. Gradually, the atmosphere regains its ability to trap the sun's heat. And with every year that passes, that sun's heat grows slightly. As our home star matures, it becomes more luminous, increasing its brightness by 6% every billion years. After 300 million years on ice, a hotter sun and better insulation means the Earth is finally able to emerge from its big freeze. Just as the white ice had reflected the sun's warmth, the newly exposed dark oceans and land surfaces absorb it, speeding up the ice's retreat. It may have only taken a few hundred years for Earth to be reborn. But all of the water, once locked away in ice, must go somewhere. And that somewhere is, of course, the oceans. Huge influxes of fresh water into the Proterozoic oceans creates a global sea level rise of massive proportions. Coastlines are drowned, and the Colombian supercontinent shrinks from its edges as newly formed land surfaces are reclaimed by the sea. And worldwide, rocks from 2 billion years ago preserve the record of this global flood, known to geologists as a marine transgression. Sedimentary rocks gradually encroach over older, weathered land surfaces, and we can reconstruct wide continental shelves bearing vast river deltas. Where water breaches hilly landscapes, sheltered bays and lagoons are formed, scalloping the edges of the continent. These shallow waters are filled with fine, nutrient-rich sediments, the product of new erosional chemistry on virgin rock surfaces. The lagoons turn a tropical blue as gentle waves lap the fractal coastline. The planet basks in the sun. The Great Flood that took place 2 billion years ago was indeed a monumental event, but it was not an apocalyptic one. For a living biosphere confined to the oceans, the drowning of the shoreline was to be celebrated, not feared. The marine transgression served to create a veritable Eden for the photosynthetic life forms that craved both the water and the light. And in this newfound paradise, they wasted no time in expanding, multiplying, and even experimenting. Since the 19th century discovery of iron-rich rocks along the southern shores of Lake Superior in North America, a thriving iron and steel industry has developed across the region. These rocks alone may be thanked for the success of the automobile industry in Detroit, which came to transform the face of America itself. So it is little surprise that these Proterozoic deposits have been the subject of much study over the last 150 years. By understanding exactly how they formed, when and under what conditions, geologists hope to unlock the Proterozoic rock record and reveal more ancient hidden treasures. And this is exactly what Stanley Tyler, professor of geology at the University of Wisconsin, happened upon in the early 1950s. Tyler and his team had dug a test pit 20 feet deep into the iron-bearing rocks of Iron River, Michigan, and retrieved samples from the deepest layers. The sample Tyler held in his hand was deep black and glinted in the sun. It was something he'd seen before, but never expected in rocks so ancient. It looked, to his educated eye, just like coal. Before their investigations could continue, however, disaster struck, and the walls of the pit collapsed, burying this mysterious sample source beneath tons of jumbled rock. So, Tyler turned to another expert in the field, a paleobotanist at Harvard named Elso Barkhorn, for a second opinion on this precious, rare sample of Proterozoic coal. Both men knew that the earliest confirmed instances of coal on Earth were much, much younger. These rocks were nearly 2 billion years old, whereas most coal is a mere 350 million years old, dating to the age of trees in the Carboniferous period. But when Barkhorn examined Tyler's samples, he confirmed the geologist's suspicions. This sample was nearly 80% pure organic carbon, and, he concluded, must have been biological in origin. Fine-scale structures within this ancient coal told of algae, not trees, being the source of such prolific productivity. Colonies of photosynthesizing bacteria grew in such numbers in the shallow Proterozoic seas that they left behind layers of coal to rival the great age of trees 1.5 billion years later. A few years later, Tyler and Barkhorn ventured out together, following the shore of Lake Superior north into Canada, in search of more evidence of this ancient algal forest. Travelling by boat, they hopped between shoreline outcrops where the gentle waves of the lake kept the marching spruce and pine forests at bay. Here, in the Gunflint Range of Ontario, they discovered dome-shaped layered structures that had been cross-cut by the waves, leaving concentric rings in the smooth rock that dipped to the water's edge. These were stromatolites, towering microcosms built layer by layer by sun-loving photosynthetic bacteria. Elsewhere, the pair discovered layers of chert, a glassy silicate rock also known as flint, which gives the Gunflint Range its name. This chert was as black as the coal Tyler had found years before, so the professors gathered as much as they could for closer study when they got back on dry land. They carefully sliced and ground paper-thin sections of the dark chert until light could pass. With this, in 1953, Stanley Tyler and Elsa Barghorn became the first to discover fossils that predated the Age of Animals. The Gunflint microbiota were the oldest fossils of the time by some 1.5 billion years. Stanley Tyler had set out to uncover wonders in the iron formations of Michigan and Ontario, and the microscopic world he revealed was wondrous beyond anything he could have imagined. The abundance of diversity of microbial fossils in the Proterozoic Gunflint cherts proved that life had wasted no time in bouncing back from the great oxygen extinction. By 2 billion years ago, the shallow seas were once again teeming with life, and the new generations were resilient to the once poisoned gas that now filled the atmosphere. Still, Proterozoic oxygen levels did not come close to modern concentrations, but there was enough for new transformations to begin at the top of the atmosphere. Ultraviolet radiation from the sun splits molecules of oxygen apart and recombines them into ozone, forming an invisible layer in the stratosphere that absorbs UV light before it reaches the surface. Without this damaging radiation washing over the land and ocean surfaces, photosynthetic life could now survive closer to the ocean's surface than ever before, even moving to colonize the wide tidal flats created by the global sea level rise. With protective ozone, the new shallow lagoons that ring the Colombian supercontinent are an algal playground, and their turquoise soon turns green with verdant blooms. In this newfound Eden, life finally has the freedom to do more than just survive. It thrives, feeding off the bounty from the earth and the sun, developing new ways of gaining the upper hand from their bacterial brothers. New, cooperative relationships between different types of bacteria are now more boldly pursued. Incomplete predation sees prey enslaved within the bodies of their masters, and the two together forge a new branch on the tree of life, as the first eukaryotes. There is no direct fossil evidence of eukaryotic cells from 2 billion years ago, and scientists aren't sure exactly when this critical transition took place. But a few curious fossils from Gabon may suggest that elsewhere, more complex cells allowed for experimentation into entirely new ways of life. One such fossil could be easily dismissed as simple gouges in the surface of a smooth grey mudstone, but closer examination of these gouges show that they are connected beneath the surface, creating tubular tunnels and tracks like some tortured ancient subway system. Although no evidence remains of the organisms that created them, organic carbon left behind seems to confirm their biological origin. At 2.1 billion years old, they are the earliest footprints in the sand, our first evidence of creatures moving by themselves. Scientists imagine they were created by a slug-like colony of amoeba-like cells moving together, tunneling through soft sediment and bacterial mats in search of nutrients or protection. Another fossil from Gabon has received a more critical review, not least because it suggests an even more radical biological experiment. At 12 centimeters across, this curious flattened form resembles a fried egg with scalloped edges. Its discoverers claim that they are the fossilized remains of multicellular organisms 1,400 million years before multicellularity really took off. Others are more skeptical, suggesting the structures could be formed by purely physical processes, and just happen to resemble lifelike structures. If they do represent an experiment in life growing large, then that experiment was a failed one. These Proterozoic fried eggs are not seen anywhere else in the world, or in any younger layers of rock. Yet, it is clear that the Earth now belongs to its life forms. There is no longer any force, chemical or physical, holding them back. The shallow, supercontinental shelf turns green as life traps carbon and stains the seafloor black with its dead. And so, on the Kola Peninsula in the Russian Arctic, the Soviet super-deep borehole penetrates the Proterozoic rocks, revealing sequences of organic-rich sediment, light-coloured volcanic rock, and frozen magma from the heart of ancient supercontinental mountains. The Russians succeeded where the Americans failed, and drilled on. For 20 years they spun up their drills and inched further and further into the crust. But they never reached the moho, never touched the mantle. The borehole bottomed out at 12¼ kilometers deep. It is sealed by an iron cap and remains the deepest mankind has ever dug. We still haven't reached the mantle, and we know much more about the surface of the moon than we do about the inside of our planet. But the Kola borehole still achieved something unexpected. From the icy wastes of the Arctic, it allowed us to peer back in time and discover paradise. You've been watching the entire history of the Earth. Don't forget to check out our partner channels, History of the Universe and Something Incredible. And we'll see you next time.